Black holes are more than just cosmic vacuum cleaners. They are the ultimate frontiers of physics, places where our deepest theories of reality simply break down and fail. This journey will explore 30 specific, unanswered questions about these mysterious objects, from their violent birth to their unknown final fate. By the end, you will see the universe through the lens of its greatest puzzles. Each unknown we uncover represents a potential revolution, a chance to rewrite the rules of physics and our place in the cosmos. We will start with the fundamental conflict at a black hole's heart, where space and time themselves are torn apart, and move all the way to their speculative role in the fate of everything. What do you believe is the ultimate truth waiting in the dark? At the absolute center of a black hole lies a prediction so extreme it shatters our understanding of reality. This is the singularity, a point of infinite density where the curvature of spacetime itself becomes infinite. According to Albert Einstein's theory of general relativity, all the mass of the collapsed star is crushed into a volume of zero size. The mathematics tells us that here, the very fabric of the cosmos is torn apart. Gravity becomes so powerful that the rules of physics as we know them simply cease to function. This isn't just a powerful object, it's a place where our equations spit out meaningless answers, where our map of the universe has a literal hole torn right through it. The singularity represents the ultimate breakdown of classical physics, a glaring sign that a deeper theory must be waiting in the wings. The conflict is stark. General relativity describes a smooth, continuous fabric of spacetime, like a perfectly stretched rubber sheet. But quantum mechanics, which governs the tiny world of particles, tells us that everything is fundamentally grainy and probabilistic. At the singularity, these two pillars of modern physics collide head-on, and neither one survives the encounter. This central unknown is not a minor detail, it's the gaping chasm at the heart of our knowledge. What truly happens when space and time reach their breaking point? The answer will require a theory of quantum gravity, a framework that can marry the immense with the infinitesimal, and that quest defines the future of fundamental physics. Yet this terrifying singularity is hidden from our view, shielded by a boundary that defines the very essence of a black hole. The event horizon is the ultimate cosmic checkpoint, the point of no return. According to Einstein's general relativity, this is not a physical surface but a geometric boundary in space. Once anything, even light, crosses this invisible threshold, its fate is sealed. There is no force in the universe powerful enough to reverse its course and bring it back out. It is a perfect one-way membrane, a stark line dividing the knowable universe from the unknowable abyss. This classical view paints the event horizon as a smooth, uneventful place. An astronaut falling toward it would, in theory, notice nothing special as they crossed it. The drama happens later as the immense gravitational forces stretch and pull them toward the central singularity. The horizon itself is just a mathematical line in the sand, a quiet gateway to oblivion. But quantum mechanics, the physics of the very small, throws a wrench into this serene picture. In the 1970s, Stephen Hawking made a revolutionary calculation. He realized that due to quantum effects occurring just outside the event horizon, black holes are not completely black. They should glow faintly with what we now call Hawking radiation. This process involves pairs of virtual particles popping into existence near the horizon. Normally, these particle pairs annihilate each other almost instantly. But if one particle falls into the black hole while its partner escapes, the black hole loses a tiny amount of mass. Over immense stretches of time, this slow leak means a black hole can theoretically evaporate and vanish. This discovery created a massive paradox. If information about what fell into a black hole is trapped forever behind the event horizon, but the black hole itself eventually disappears, what happens to that information? Is it truly destroyed, violating a fundamental law of quantum physics? or does it somehow leak out, scrambled in the Hawking radiation? This question, the black hole information paradox, has fueled decades of fierce debate. One radical proposal to resolve it suggests the event horizon is not peaceful at all. It might be a seething wall of ultra-high energy particles, a quantum firewall that would incinerate anything attempting to cross. In this view, the point of no return is also a point of immediate destruction, contradicting the smooth geometric prediction of relativity. So which picture is real? Is the event horizon a silent geometric gateway as Einstein taught us, or is it a violent, fiery wall as some quantum theories suggest? Or is it something else entirely, a structure we cannot yet conceive? The true nature of this boundary remains one of the greatest unknowns in modern physics, a direct battleground between our two most successful theories of reality. This faint glow from the abyss is Hawking radiation, a theoretical whisper that challenges everything we thought we knew. Stephen Hawking's brilliant insight was to apply the strange rules of quantum mechanics to the edge of a black hole. In the quantum world, empty space is not truly empty. It is a seething sea of potential where pairs of virtual particles and antiparticles constantly flicker into and out of existence, borrowing energy from the universe for the briefest of moments before annihilating each other. Normally, this dance leaves no trace, but at the very precipice of an event horizon, a cosmic robbery can occur. One member of the particle pair might fall across the boundary, captured forever by the black hole's gravity. Its partner, now suddenly real and alone, is free to escape into the wider universe. To an outside observer, it appears as a faint stream of radiation emanating from the black hole itself. The energy for this creation comes from the black hole's own mass. So, incredibly, by emitting this faint glow, the black hole slowly loses weight. Over timescales that dwarf the current age of the universe, a black hole not fed by new material could theoretically evaporate completely, vanishing in a final, silent puff. This prediction is beautiful and profound, but it opens a chasm of unknowns. The first is a question of identity. Does this escaping radiation carry any signature, any hidden code of the matter that originally fell in? Imagine throwing a grand piano, a library of books, and a star into a blazing fire. The heat and light given off tell you nothing about what was burned. Hawking's original math suggested the radiation was purely thermal, a generic heat signature with all the original information scrambled beyond recovery. This violates a core tenet of quantum physics, which states that information can never be truly destroyed, only transformed. This is the heart of the information paradox. If the information is lost forever when the black hole evaporates, our understanding of reality is fundamentally flawed. Many physicists now suspect the information must be encoded in some fantastically complex way within the Hawking radiation itself. But how? Is it imprinted on the radiation like a hologram, or is it tangled in correlations so subtle we cannot yet perceive them? Resolving this is not just about black holes, it is about whether the universe itself keeps a perfect quantum record of everything that happens. The final, daunting unknown is one of detection. Hawking radiation is unimaginably faint for any black hole massive enough to form naturally. For a black hole with the mass of our Sun, the temperature of the radiation would be a fraction of a degree above absolute zero, utterly drowned out by the cosmic microwave background, the leftover heat from the Big Bang. To detect it directly, we would need to find a primordial black hole, one potentially formed in the early universe with much less mass, and thus a much hotter, brighter Hawking glow. We have never confirmed such an object exists, so we are left with a breathtaking idea, a theoretical prediction that reshapes our view of cosmic fate, yet one that remains just beyond the edge of our observational reach. It is a ghostly signal from the void, holding the keys to quantum gravity and the fate of information, waiting for a future generation to finally hear its whisper. This paradox is not just a technical puzzle, it is a direct threat to the foundation of quantum physics. The principle of unitarity is a cornerstone of the quantum world. It states that the evolution of a quantum system is always reversible. Information about the initial state of any system, whether it is a single particle or an entire star, is never truly lost. It may be scrambled and transformed beyond recognition, but in theory, given enough computing power and the right laws, you could always rewind the tape. A black hole, according to Hawking's original calculation, appears to burn that tape. If you take a collection of unique objects with vast amounts of specific information, toss them into a black hole, and wait for it to evaporate into a featureless cloud of Hawking radiation, what emerges seems to carry no trace of what went in. The specific becomes generic. The story of what fell in is erased from the universe. This violates unitarity, suggesting that our most precise description of reality is fundamentally incomplete. The stakes could not be higher. If information can be destroyed in black holes, then the logical, predictable framework of quantum mechanics fails at the cosmic scale. This has forced physicists to propose radical, mind-bending solutions, each rewriting our concept of reality in a different way. One leading idea is the holographic principle. It suggests that all the information describing everything within a three-dimensional volume of space, like the interior of a black hole, is actually encoded on its two-dimensional boundary, the event horizon. Think of it like a cosmic DVD. The three-dimensional movie you experience is actually stored on a flat, two-dimensional surface. In this view, the information of what fell in is not lost inside the singularity, but is smeared and preserved on the horizon surface, eventually leaking out in the Hawking radiation. Another proposal is black hole complementarity. This idea argues that the question of what happens at the horizon has no single answer. It depends entirely on who is observing. For an astronaut falling in, according to general relativity, they cross a smooth horizon and meet their fate later at the singularity. For an outside observer watching forever, the astronaut's information appears to be smeared and heated on the horizon, never actually crossing it. Both stories are true simultaneously from their own perspectives, and no single observer can ever see both to spot a contradiction. Then there are more speculative ideas like the possibility of Planck-scale remnants. Perhaps black holes do not evaporate completely. They might shrink down to a tiny, stable speck, a remnant with almost infinite density that holds all the original information locked inside forever. Or maybe our understanding of spacetime itself is wrong, and the interior of a black hole is not a separate place at all, but is somehow mathematically equivalent to a highly complex state of the radiation outside. The field is brilliantly unsettled. Each proposed solution requires us to abandon an intuitive picture of how the universe works, trading one mystery for another. The true resolution will likely come from a complete theory of quantum gravity, a framework we are still grasping toward. Until then, the information paradox stands as a monument to our ignorance, a clear sign that some of our most cherished ideas about reality are, at best, incomplete glimpses of a much stranger truth. But if we could somehow survive the journey past the event horizon, what would we actually find inside? The popular image is a one-way trip to a central point of infinite density, but the mathematical reality might be far stranger and less certain. General relativity provides a map, but that map contains regions where its own directions become unreliable. One such feature is the inner horizon, a theoretical boundary inside a rotating black hole. While the event horizon is the point of no return for escaping, the inner horizon is often described as the point of no return for surviving. According to the equations, as you cross this inner boundary, the very nature of space and time might flip. Some calculations suggest that tidal forces, which stretch you vertically and compress you horizontally, could become infinite here, a phenomenon called the Cauchy horizon instability. In this view, the inner horizon is not a gateway but a wall of infinite gravitational fury, shredding anything that reaches it. This would make the central singularity unreachable, protected by its own violent frontier. Yet other models challenge this grim picture. They propose the inner horizon could be a place of extreme but finite chaos, a turbulent region where the infalling material from the black hole's entire history piles up, creating a storm of radiation and energy. You would not find serene darkness but a blinding, chaotic maelstrom. This leads to an even more speculative idea. The elegant equations for a rotating black hole, known as a Kerr black hole, mathematically describe a gateway at its core. This is the Einstein-Rosen bridge, more popularly known as a wormhole. The math suggests the crushing singularity might be avoided, and the interior could funnel into a tunnel connecting to another point in space, or even another universe entirely. It is a breathtaking possibility straight from the pages of science fiction, but there is a profound catch. These bridges, according to our current physics, are almost certainly unstable. They would snap shut in an instant unless held open by a form of exotic matter with negative energy, something we have never observed and is purely hypothetical. Every description of a black hole's interior, from the chaotic inner horizon to the speculative wormhole, remains in the realm of mathematical speculation. We have no observational data, no experiments, and no way to test what lies beyond that ultimate veil. The interior is a blank canvas where our most advanced theories paint wildly different pictures. It forces us to confront a humbling truth. We are describing the geography of a place that may, by its very nature, be indescribable. What we call the inside might not be a place at all in any familiar sense, but a radical transformation of reality itself, where concepts like here, there, before, and after lose all meaning. These cosmic mysteries only deepen when we scale up to the titans that anchor entire galaxies. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not merely large, they are incomprehensibly vast, containing the mass of millions or even billions of suns compressed into a region smaller than our solar system. Their existence is a profound puzzle, and their origin story is one of the great detective cases in modern astronomy. The central question is one of time. We observe these monsters fully formed in galaxies that existed when the universe was less than 1 billion years old, a mere blink in cosmic history. How did something so massive assemble so quickly? The universe simply did not have enough time, under the rules we understand, for a regular star to die, leave behind a small black hole, and then slowly eat its way up to billions of solar masses. The math does not add up, so astronomers are forced to consider more dramatic, rapid birth scenarios. One leading theory is the direct collapse model. Imagine the early universe not yet filled with glittering galaxies, but with vast, pristine clouds of hydrogen and helium gas. Under just the right conditions, a giant cloud, perhaps hundreds of thousands of times the mass of our Sun, could have collapsed under its own weight. But instead of fragmenting into many stars, it collapses in one catastrophic, monolithic event. No supernova, no brilliant star death, just a silent, direct implosion into a massive black hole, seed already thousands of times heavier than any star could produce. This seed would then have a tremendous head start on its growth. Another path involves those smaller stellar black holes as seeds. In the dense, chaotic nurseries of the first star clusters, these black holes could have rapidly merged together, sinking to the center of the young galaxy and beginning a frantic feast. They would have gorged on the abundant gas swirling around them, growing at astonishing rates in a process called super-Eddington accretion, where material falls in faster than our standard models predict. There are even more exotic candidates for these original seeds. Could they be primordial black holes, formed not from stars but from the intense density fluctuations in the first moments after the Big Bang itself? If such objects with the right mass existed, they could have been present from the very beginning, serving as ready-made anchors for galaxies to form around. The challenge is that this era of first light and first black holes is shrouded in cosmic fog. We are trying to witness events that occurred over 13 billion years ago at the very edge of our observational reach. Our best tools, like the James Webb Space Telescope, are now peering into this dawn, searching for the faint, reddened glow of gas swirling around these infant giants. Each new observation is a clue, helping us rule out theories and piece together a plausible history. The birth of these supermassive black holes was not just an isolated event. It was a foundational act that shaped the destiny of every galaxy they inhabit, governing the orbits of stars and perhaps even putting a limit on galactic growth. Their mysterious origins are woven into the very fabric of cosmic history. While supermassive black holes command the centers of galaxies, a ghostly counterpart might be hiding in the vast spaces between the stars. These are primordial black holes, hypothetical objects that could have formed not from dying stars, but from the raw, churning energy of the Big Bang itself. In the first frantic fractions of a second after the universe began, space was not smooth and uniform. It was a seething quantum foam where density could vary wildly from one tiny region to the next. In places where the pressure and density spiked high enough, a pocket of space could have directly collapsed, pinching off to form a black hole. This bypasses the need for a star entirely, meaning these objects could have any mass from smaller than an asteroid to larger than a planet. Their size is not limited by stellar physics, but by the conditions of the infant cosmos. This opens a breathtaking possibility. Could these ancient, unseen black holes account for the mysterious substance we call dark matter? For decades, astronomers have known that galaxies and clusters hold together with far more gravity than their visible stars and gas can provide. Something invisible, making up about 85% of all matter, must be providing the extra gravitational glue. Primordial black holes are a compelling candidate because they would be dark, stable, and would have formed early enough to sculpt the growth of galaxies. They would be the universe's original shadow, woven into its fabric from the very beginning. The hunt for these phantoms is a masterclass in cosmic detective work. Since they would not emit light, we must search for the subtle ways their immense gravity warps the fabric of reality around them. One method is gravitational microlensing. If a primordial black hole drifted precisely between Earth and a distant star, its gravity would act as a lens, bending the starlight and causing the star to temporarily brighten in a very specific pattern. Surveys scanning millions of stars have watched for these telltale flashes, placing strict limits on how many such objects of certain masses could be drifting unseen through our galactic neighborhood. Another ingenious search looks at the dense corpses of dead stars called neutron stars. If a tiny, asteroid-mass primordial black hole were to collide with a neutron star, it would be swallowed whole. The impact would trigger vibrations in the neutron star that could, in theory, be detected as a burst of gravitational waves. Even more dramatically, some models suggest a small black hole could get stuck inside the neutron star, slowly consuming it from the inside out over millions of years. The star would glow with an unusual heat from this internal digestion, a potentially observable signal. Finding even one primordial black hole would be a discovery of monumental importance. It would provide a direct window into the conditions of the universe in its first fleeting moments, offering clues about the physics of inflation and quantum gravity that are otherwise inaccessible. It could solve the dark matter puzzle, revealing that a portion of the universe's missing mass is not an exotic particle, but ancient knots of spacetime itself. Most profoundly, it would confirm that black holes are not just endpoints of stellar life, but fundamental features of cosmic birth, present at the dawn of everything. Their existence would mean our universe is literally built upon a hidden architecture of unimaginable density, a secret history written in gravity alone. The journey into a black hole is often described with a single, vivid word: spaghettification. It is the process where the difference in gravity between your head and your feet becomes so extreme that you are stretched into a long, thin strand of atoms. But this dramatic end is only one side of the story, and the full picture is fractured by a fundamental conflict in perspectives. What truly happens depends entirely on who is telling the tale. For the brave, or perhaps foolish, astronaut making the plunge, the journey past the event horizon might be surprisingly uneventful, at least at first. According to Einstein's general relativity, the event horizon is not a physical barrier. If the black hole is large enough, like the supermassive one at our galaxy's center, the tidal forces at the horizon are gentle. You could cross it without feeling a sudden jolt or seeing a flashing sign. From your point of view, you continue falling inward, drawn toward the central mysteries we have discussed. The spaghettification occurs later as you get closer to the crushing heart of the singularity. Your own story ends there, but for your colleagues watching from a safe distance on a mothership, your story unfolds in a completely different and deeply strange way. Due to the extreme gravitational time dilation near the event horizon, time for you appears to slow down drastically from their perspective. As you approach that invisible boundary, your clock seems to tick slower and slower. Your signals back to them become more and more delayed, stretched out over longer intervals. From their viewpoint, you never quite seem to reach the horizon. You instead appear to slow down, freezing in place just outside it, growing ever dimmer and redder as the light struggling to escape loses energy. This leads to a profound and unresolved debate. Does the outside observer ever actually see you cross the event horizon? Some interpretations of the mathematics suggest they do not in any finite amount of time. You would appear as a fading, red-shifted ghost, eternally approaching but never vanishing. This creates a bizarre paradox. You experience crossing and meeting your fate, while the universe outside records you as forever trapped on the threshold. So which perspective is real? Physics has no privileged frame of reference, meaning both stories could be valid from their own viewpoints. This is the essence of black hole complementarity. But it forces a difficult question. What would a powerful telescope actually see if we pointed it at someone falling in? Would it show this frozen, fading image? The answer is more subtle. The image would not simply freeze like a paused video. As the falling object gets closer to the horizon, the light it emits takes longer and longer to climb out. Each subsequent photon has a harder journey. From our distant vantage point, we see the object in extreme slow motion. Its last detectable light, emitted just before crossing, might take thousands or millions of years to finally reach us. But there is another factor. That light is not just delayed, it is also sapped of energy, shifted to longer, redder wavelengths, eventually fading into infrared and then radio waves until it becomes too faint to detect against the background noise of the cosmos. Furthermore, the object itself would appear to dim rapidly because fewer and fewer photons manage to escape the gravitational well. So what a telescope records is not a frozen snapshot, but a rapid dimming and reddening, followed by an apparent disappearance as the last struggling photons arrive. The object seems to vanish, not because it has been destroyed at a fiery wall, but because its final signal has finally, after eons, dribbled out into the universe. This duality of experience lies at the heart of modern black hole physics. It challenges our basic notion of a single, objective reality. It suggests that in the most extreme environments, the story of what happens cannot be told from a single point of view. The fate of the falling object is not one story, but two, and reconciling them may require us to accept that reality itself is, in a deep sense, observational. The absolute rule that nothing escapes a black hole is a cornerstone of its terrifying reputation. Yet physics loves to find cracks in absolute rules, and black holes are no exception. While it remains true that no object or light signal can ever travel back out across the event horizon once it has fallen in, There are narrow, brilliant theoretical windows for extracting something precious from the grip of a black hole: energy. The most famous method is the Penrose process, a concept that sounds like science fiction but is grounded firmly in the mathematics of rotating black holes. Imagine a space adventurer daring to fly just outside the event horizon of a spinning black hole, a region called the ergosphere. Here, spacetime itself is dragged around so violently by the black hole's rotation that it is impossible to stand still. The adventurer fires a projectile or perhaps even splits a container of fuel into two pieces. One piece is aimed to fall into the black hole, but on a trajectory that steals some of the black hole's immense rotational energy. The other piece, with a carefully calculated boost from this cosmic theft, escapes back out to infinity. The result is that the escaping piece carries away more energy than the original object had, while the infalling piece carries negative energy into the black hole, effectively slowing its spin. The black hole loses a tiny amount of its rotational energy, which the adventurer captures. This is not matter escaping from inside the event horizon. It is energy being mined from the twisted spacetime just outside it. Another speculative possibility involves the quantum realm. Quantum tunneling is a bizarre effect where a particle can appear on the other side of a barrier it classically should not be able to cross, like a ghost walking through a wall. Some physicists have pondered whether, on unimaginably long timescales, information itself could quantum tunnel out from inside a black hole. This would not be a macroscopic escape, but a probabilistic whisper, a potential loophole in the classical law of imprisonment. It remains highly controversial and unproven, but it highlights how quantum mechanics constantly challenges our classical intuitions. Then there is the most radical hypothesis of all, the white hole. If a black hole is a region of space from which nothing can escape, a white hole is its theoretical opposite, a region from which nothing can enter. Matter and energy would only ever pour out of it. In some solutions to Einstein's equations, a black hole's interior can be mathematically connected to a white hole in a different part of spacetime or even a different universe. This forms the other end of an Einstein-Rosen bridge or wormhole. However, white holes are believed to be violently unstable if they could form at all, and no observational evidence for one has ever been found. They represent a tantalizing mathematical symmetry, a beautiful idea that the cosmos might balance its most absolute traps with impossible fountains. The critical distinction in all these ideas is between energy and matter. The Penrose process extracts energy from a black hole's environment, not from its interior vault. Quantum tunneling, if real, might allow information to leak, but not in any useful, controllable way. And white holes are entirely separate objects, not escape routes from existing black holes. So the classical rule stands firm for any traveler or signal, but the universe, in its infinite creativity, seems to have left a few theoretical receipts lying around, suggesting that even the darkest prisons might slowly leak their wealth into the cosmos, one stolen quantum of spin at a time. Even as a black hole pulls everything toward its center, it can also unleash the most powerful directed beams in the universe. These are relativistic jets, colossal geysers of superheated plasma that scream from the poles of certain black holes at nearly the speed of light, stretching for thousands or even millions of light years into intergalactic space. They are a spectacular contradiction, a testament to the fact that black holes are not just sinks, but also the most formidable engines in creation. The raw power for these jets comes from the chaos just outside the event horizon. When a black hole is actively feeding, material from a companion star or a galactic gas cloud forms a swirling, frenzied disk called an accretion disk. Friction within this disk heats it to millions of degrees, making it glow brilliantly across the electromagnetic spectrum. But some of that material, instead of falling in, gets caught in a cosmic slingshot. The prevailing theory involves the black hole's spin and immensely powerful magnetic fields that are twisted and amplified by the churning disk. These magnetic fields act like the rigid spokes of a wheel, channeling some of the infalling plasma and launching it outward along the black hole's rotational axis, the only path of least resistance. This creates two opposing beams, focused and accelerated to relativistic speeds. Yet the precise ignition switch for this process remains one of astrophysics' greatest puzzles. How exactly do magnetic fields extract so much energy from the system? Where and how are particles accelerated to such phenomenal speeds? We see the stunning effects, but the detailed engine blueprint is missing. The scale of these jets is almost impossible to comprehend. From a stellar mass black hole in a binary system, the jet might stretch across a few light years. But from a supermassive black hole in an active galactic nucleus, the jet can punch entirely out of its home galaxy and far into the intergalactic void, carrying energy equivalent to the output of billions of stars. These are not gentle streams, they are tsunamis of radiation and particles that can sterilize entire regions of a galaxy, halting star formation, and yet they can also trigger it in surrounding gas clouds, playing a dual role as both destroyer and creator. Observing these different scales offers vital clues. The jets from small stellar black holes in our galaxy can change over days or weeks, giving us a fast motion view of their dynamics. The jets from distant supermassive black holes are frozen in time from our perspective, but their immense structures reveal the long-term effects of these powerful beams. By studying both, astronomers hope to find the universal principles that govern how black holes, regardless of size, can focus such raw gravitational power into a lightsaber-sharp beam that scars the cosmos itself. The immense power of a black hole's jet is a spectacle of its active life, but its most violent and revealing moment comes at its death, or more precisely, its marriage to another. When two black holes are locked in a mutual gravitational embrace, they perform a final, catastrophic dance that shakes the very fabric of the cosmos. This process, the coalescence of a binary black hole system, unfolds in three distinct acts, each with its own cosmic signature. It begins with the in-spiral, a slow, elegant waltz that can last for millions of years. As the two black holes orbit one another, they lose energy by radiating gravitational waves, those ripples in spacetime predicted by Einstein. This loss of energy causes their orbits to tighten, and as they spiral closer together, their speed and the frequency of the gravitational waves they emit increase. This phase is beautifully described by general relativity, and for a long time it was all we thought we could model. But the final moments are where the true mystery and violence reside. The second act is the merger itself. When the black holes get so close that their event horizons touch, they plunge together in a fraction of a second. This is a realm of extreme, nonlinear gravity where the simple equations of the in-spiral break down completely. The two singularities, the two knots of infinite density, become one. Their event horizons stretch, merge, and form a single, highly distorted and lopsided black hole. This moment is the most computationally intense problem in all of astrophysics, requiring simulations on the world's most powerful supercomputers to even approximate. We cannot see light from this event, but we can feel it as it unleashes a thunderclap of gravitational waves, a burst of energy that can briefly outshine every star in the observable universe combined. Then comes the third and final act, the ringdown. This is the newborn black hole's cry as it settles into a stable form. Imagine striking a bell. It vibrates, ringing at specific tones that depend on the bell's shape and material. A black hole does the same thing in spacetime. The distorted, lumpy object vibrates, shedding its imperfections not as sound, but as gravitational waves at specific frequencies, known as quasi-normal mode. This ringdown is the black hole's way of announcing its final mass and spin to the universe. By analyzing the frequency and decay rate of these waves, scientists can test general relativity with unprecedented precision, checking if the object that formed behaves exactly as Einstein's theory predicts a black hole should. Yet, the nonlinear chaos of the merger phase remains a profound frontier. The physics of two singularities becoming one, the behavior of spacetime at that moment of contact, is a turbulent mystery hidden behind the event horizon of our understanding. Each gravitational wave signal we detect is a Rosetta Stone from this dark process, a complex message we are still learning to decode. It tells us not just that black holes merged, but offers a fleeting glimpse into the extreme geometry of gravity itself, written in the language of rippling spacetime. The mathematics of a spinning black hole is described by a beautiful set of equations known as the Kerr metric. Unlike the simpler, non-rotating Schwarzschild black hole, a Kerr black hole drags spacetime around with it, creating a swirling vortex of reality. This rotation is quantified by a parameter simply called spin, represented by the letter A. This number can range from 0 for a black hole that does not spin at all, up to a theoretical maximum value of 1. At this mathematical limit, the event horizon shrinks to its smallest possible size, and a region called the ergosphere, where nothing can remain stationary, grows larger. The very geometry of the black hole becomes extreme, with the inner horizon moving perilously close to the event horizon. But can a black hole actually reach this theoretical maximum? The equations allow it, but nature often has other plans. The primary way a black hole gains spin is by feeding. As material falls in from an accretion disk, it carries angular momentum, spinning the black hole up like a child's top being pushed. However, this process has a natural break. If matter falls in from a random direction, it can just as easily slow the spin as speed it up. To reach near maximum rotation, the black hole must be fed by a disk that is perfectly aligned and stable over vast stretches of time, allowing a steady, one-directional transfer of momentum. Another dramatic path to high spin is through a merger with another black hole. The complex dance of two orbiting black holes can result in a final black hole with a tremendous amount of spin, depending on the alignment of their original rotations. Yet even here, the gravitational waves blasted out during the merger carry away angular momentum, preventing the remnant from quite reaching the absolute limit. So the open question is stark. Do any physical processes in the universe allow a black hole to hit a spin of exactly 1? Or is there always some loss, some instability, or some unknown quantum gravitational effect that acts as a cosmic governor, keeping the spin just below the mathematical ceiling? To answer this, we must look out into the cosmos and measure. Astronomers have developed ingenious techniques to probe black hole spin, primarily by studying the X-rays emitted from the inner edge of their superheated accretion disks. As matter spirals inwards, it gets hotter and brighter, emitting radiation just outside the event horizon. For a non-spinning black hole, this inner edge is relatively far out. But for a rapidly spinning black hole, the dragging of spacetime allows matter to orbit much closer in. By carefully analyzing the spectrum of this X-ray light, specifically looking for distortions caused by the immense gravity and relativistic effects, scientists can estimate how close that inner edge is and therefore calculate the black hole's spin. The results have been astonishing. Several black holes, both stellar mass and supermassive, have been measured with spins exceeding 0.9, incredibly close to the maximum. Some, like the famous black hole in the binary system GRS1 915+105, appear to be spinning at least 98% of the maximum possible rate. These observations push right up against the edge of our theoretical understanding. They tell us that nature can create engines of breathtaking efficiency, black holes that have been spun up by a consistent long-term feast. But they also sharpen the mystery. Is that last 2% an observational uncertainty, or is it a fundamental barrier? Could a black hole ever be spun so fast that its inner horizon and event horizon merge, causing a mathematical breakdown known as a naked singularity, an object with no event horizon at all? Most physicists believe the cosmic censorship hypothesis forbids such a thing. that nature always hides singularities behind an event horizon. If that is true, then a spin of exactly one may be a forbidden state, a mathematical ideal that the universe, in all its violent creativity, can approach but never quite touch. This mathematical simplicity is both elegant and deeply unsettling. According to the famous no-hair theorem, a black hole in the classical universe of general relativity is the most boring object imaginable. It possesses only 3 distinguishing features you could ever measure from the outside: its mass, its electric charge, and its spin. That is it. No texture, no scars, no memory of what fell in. Whether you feed it a cloud of hydrogen, a library of encyclopedias, or 1,000 solar systems, the resulting black hole would be utterly indistinguishable from any other with the same mass, charge, and spin. All the rich, complex information about its ingredients is permanently lost behind the event horizon, erased from the observable universe. The black hole is said to have no hair, meaning no extra details or frills. It is a perfect, featureless bald spot in the fabric of reality. This theorem is a cornerstone of classical black hole physics, a statement of ultimate simplicity emerging from ultimate chaos. Yet many physicists suspect it cannot be the full story, that this cosmic baldness might be an illusion. The first cracks in this principle appear when we introduce quantum mechanics. While the classical black hole may be bald, the quantum fields around it certainly are not. Consider a black hole with an electric charge. The electric field it produces is not hair in the no-hair theorem sense, because charge is one of the 3 permitted properties. But what about other, more subtle fields? Could a black hole retain a faint imprint of a magnetic field from the star that birthed it? Or could certain types of exotic matter, theoretical constructs that violate standard energy conditions, cling to a black hole and give it a kind of permanent quantum hairstyle? These possibilities suggest that the no-hair theorem might be a classical approximation, and that a full quantum gravitational description of a black hole would reveal a complex, information-rich structure, perhaps encoded on its event horizon. This is where observation becomes our ultimate arbiter. The quest to find black hole hair is not philosophical, it is an experimental race. The most promising tool for this search is the detailed study of gravitational waves, the ripples from black hole mergers. According to the no-hair theorem, the ringdown of a newly merged black hole, its final settling vibrations, should consist of a very specific set of tones that depend only on its final mass and spin. Any deviation from this predicted spectrum would be a smoking gun, a sign that the black hole has some extra property, some hidden hair that is affecting its vibration. It would be like listening to a bell ring and hearing an unexpected harmonic, telling you the metal has an impurity the manufacturer did not list. Current detectors like LIGO and Virgo are not yet sensitive enough to perform this test with high precision, but future observatories, both on Earth and in space, are being designed with this exact goal in mind. They will listen to the dying echoes of colliding black holes with exquisite detail, searching for any whisper of an extra tone. Finding such a deviation would be a monumental discovery. It would not just be about adding a new property to a list, it would directly challenge the pure, geometric vision of general relativity, forcing a revision of our most fundamental ideas about gravity, information, and what a black hole truly is. The universe may yet prove that its darkest objects are not simple, bald prisons, but complex entities wearing a subtle, gravitational crown we are only just learning how to see. The sheer mass of a supermassive black hole is not an isolated statistic, it holds a cosmic secret. Astronomers have discovered a remarkable and precise correlation. The more massive the central black hole, the more massive the central bulge of stars in its host galaxy. This is not a loose trend, it is a tight, mathematical relationship that spans billions of light years and billions of years of cosmic history. It is as if the galaxy and its dark heart grew up together, their fates intimately entwined from the very beginning. This correlation is one of the most profound clues we have about how the universe builds its largest structures, and it points to a deep, unknown symbiosis. The central question is one of cause and effect, a cosmic chicken and egg puzzle on a galactic scale. Does the black hole control the galaxy, or does the galaxy control the black hole? One compelling theory casts the supermassive black hole in the role of a galactic regulator. In this scenario, when the black hole is actively feeding and powering its brilliant quasar phase and relativistic jets, it does not just shine, it screams. The immense energy pouring out acts as a form of feedback, heating the surrounding gas in the galaxy to such high temperatures that it cannot cool down and collapse to form new stars. This process, known as quenching, could effectively shut off star formation in the galaxy's central regions. The black hole, by its own furious appetite, starves the galaxy of its future stellar generations. It is a powerful, self-limiting cycle. The more the black hole eats and grows, the more energy it releases, eventually shutting down the very fuel supply that feeds it. This could explain the correlation. The final mass of the black hole is a record of how much energy it took to quench its host, but the story could be told in reverse. Perhaps the galaxy itself is in the driver's seat. The overall gravitational potential of the galaxy, the depth of its central well, may determine how much gas can funnel down to the core to feed the black hole. In this view, the black hole is merely a passenger growing to a size proportionate to the banquet the galaxy provides. The correlation then is not about control, but about shared resources. Both the stellar bulge and the black hole simply reflect the total mass and history of the available material in the galactic center. The truth likely lies in a dynamic back-and-forth dance, a co-evolution where each partner influences the other across cosmic time. Early in a galaxy's life, chaotic mergers and abundant gas feed both a frenzy of star formation and a voracious black hole. The black hole's subsequent feedback may then sculpt the galaxy's later development, preventing it from growing too large too fast. This intricate feedback loop is the missing chapter in the story of cosmic evolution. We see the stunning correlation, the final result of this billion-year tango, but we are still piecing together the precise steps. Solving this mystery means understanding not just how black holes work, but how they write the destiny of every shining city of stars they call home. The mathematics that allows a black hole to spin also contains a breathtaking possibility hidden within its equations. Deep inside the theoretical structure of a rotating black hole, the Kerr metric, there is not just a singularity but a gateway. This is the Einstein-Rosen bridge, more commonly known as a wormhole. The equations of general relativity do not forbid its existence. They describe a tunnel, a shortcut through the fabric of spacetime that could, in theory, connect two distant points in our universe or even bridge to an entirely different cosmos altogether. It is a concept that fuels our deepest science fiction dreams of instantaneous travel and cosmic exploration. But the journey from a line in an equation to a functioning stargate is fraught with insurmountable barriers. The first and most profound problem is stability. The wormholes described by the Kerr metric and similar solutions are not traversable. They are often called non-traversable wormholes for this exact reason. They would snap shut or pinch off in an instant far faster than even a beam of light could travel through. The space-time tunnel collapses before anything can pass. To hold such a tunnel open, to make it a practical highway and not a cosmic cul-de-sac, you would need a form of matter with truly bizarre properties. This is exotic matter, a theoretical substance that possesses negative energy density. Unlike everything we have ever observed, this material would have to exert a kind of negative gravity, a repulsive pressure that pushes the walls of the wormhole apart and prevents its catastrophic collapse. We have no evidence such a substance exists or could be manufactured. Even if we could somehow find or create it, the engineering challenges are beyond any conceivable technology. The energies required to manipulate spacetime on this scale, to stabilize a macroscopic wormhole, are literally astronomical, likely requiring the mass energy of a star or more. Then there is the issue of causality and the potential for time travel paradoxes. Some wormhole configurations, if made stable, could theoretically be manipulated to create closed time-like curves, paths through spacetime that loop back on themselves, allowing travel into one's own past. This introduces infamous logical problems like the grandfather paradox, where you could potentially prevent your own existence. Most physicists believe the universe has a fundamental rule, often called the chronology protection conjecture, that prevents such paradoxes from occurring. The prevailing view is that quantum effects would become infinitely destructive at the threshold of creating a time machine, destroying the wormhole or making it impassable. So where does this leave us? The existence of wormholes remains a profound unknown at the razor's edge where general relativity meets quantum field theory. They are mathematically elegant possibilities that highlight the flexibility and strangeness of Einstein's description of gravity. Yet they are almost certainly not the practical time machines or interstellar shortcuts of popular fiction. They serve as a powerful reminder that the universe's rulebook allows for wonders we can write down but may never walk through. Their true value may not be as blueprints for engines, but as thought experiments that pressure test our theories, forcing us to ask what is truly possible when spacetime itself becomes a material to be shaped. While wormholes stretch our imagination to cosmic scales, the opposite end of the spectrum holds mysteries just as profound. What is the smallest a black hole could possibly be? Our journey into the quantum realm suggests there is a fundamental lower limit, a point where gravity and quantum mechanics collide to define the tiniest knot spacetime can tie. This theoretical boundary is linked to the Planck mass, an incredibly small quantity derived from fundamental constants of nature. It is roughly the mass of a grain of dust, but compressed into a volume a billion times smaller than an atomic nucleus. At this scale, the Compton wavelength of a particle, which defines its quantum fuzziness, becomes comparable to its Schwarzschild radius, the size its event horizon would be if it were a black hole. This is the domain where quantum gravity must take over, and a microscopic black hole could, in theory, flicker into existence. It represents the absolute edge of our physical understanding, the smallest possible object that could still be called a black hole under any known law. This idea leads to a startling possibility, one that has sparked both excitement and careful scrutiny in the world of physics. Could we create such a microscopic black hole here on Earth? Some theories, like certain models of string theory, suggest that if our universe has hidden extra-spatial dimensions, gravity could become much stronger at incredibly tiny scales. In such a scenario, the immense energies achieved in the world's most powerful particle accelerators, like the Large Hadron Collider, might be enough to squeeze particles together so violently that they form a transient microscopic black hole. It is a breathtaking thought that our greatest machines might briefly touch the fabric of quantum gravity. However, there is a crucial and reassuring detail about these hypothetical objects. A black hole with a mass near the Planck scale would be governed by Hawking radiation in its most extreme form. It would not be a stable, hungry monster. Instead, it would evaporate in a spectacular flash of particles within a time span so short it is almost meaningless, far less than a trillionth of a second. Any such creation would be a fleeting quantum event, a spark in a detector, not a threat. Despite extensive searches, no evidence for these phenomena has been found, suggesting that if extra dimensions exist, they are curled up at sizes even smaller than our current collisions can probe. This theoretical landscape of the ultra-tiny stands in stark contrast to the black holes we actually observe in the cosmos. The smallest stellar mass black holes we have confidently detected are born from the collapse of massive stars, and they weigh in at several times the mass of our Sun. Nature, it seems, has a preferred starting size for its gravitational traps, one far, far larger than the Planck scale. The gap between these observed giants and the hypothetical quantum specks is astronomically vast. It tells us that while the laws of physics might permit black holes of almost any size, the natural processes of our universe favor a dramatic and violent birth, one that leaves behind an object of substantial gravitational might. The search for the smallest possible black hole is therefore a journey to the frontier of theory, a quest to understand where gravity becomes a quantum force and whether the fabric of spacetime can be punctured on scales we are only beginning to imagine. The quest to understand the smallest black holes leads us directly to the heart of the greatest theoretical challenge in all of physics. To truly describe what happens at the event horizon, we cannot rely on general relativity alone, nor can we use quantum mechanics by itself. We need a theory that unites them, a framework of quantum gravity. This is not a minor adjustment, it is the primary mission of modern theoretical physics, and the event horizon is its ultimate testing ground. In our current picture, the horizon is a smooth, geometric boundary, but quantum mechanics tells us that at the tiniest scales, nothing is smooth. Empty space seethes with quantum fluctuations, where energy borrows from nothingness to create temporary pairs of particles. Apply this principle to the horizon, and that perfect boundary must become a stormy, roiling sea. It would not be a sharp line, but a fuzzy, probabilistic region, flickering and churning on the scale of the Planck length, a distance so small it is a billion times smaller than an atom. Some theories propose the horizon is not even continuous, but is made of discrete quantum units of area, like pixels on a cosmic screen. This quantum fuzziness could be the key that unlocks every paradox we have faced. Think of the information paradox. If the horizon is a blurry, fluctuating surface, then information from what fell in might not be trapped behind a perfect wall. It could be imprinted on this quantum fuzz, scrambled into the microscopic structure of the horizon itself, and then slowly radiated away as the black hole evaporates through Hawking radiation. In this view, information is never truly lost. It is just transformed in an incredibly complex way we do not yet fully understand. Even the terrifying singularity at the center might be resolved by a complete theory of quantum gravity. The infinite density predicted by classical physics is almost certainly a sign that the theory has broken down. Quantum effects, perhaps a tremendous repulsive force or a transition to a new state of spacetime, could prevent the collapse to a true infinity. The singularity might be replaced by an extremely dense but finite core of quantum matter, a place where spacetime is reborn into something new rather than torn apart. This is the profound promise of quantum gravity. It would not just tweak our equations, it would revolutionize our concept of reality at its most extreme. It aims to show us that the horizon is not an end but a transformation, and that the black hole is not a destroyer of information but its most secure and complex vault. The entire cosmos in this light might be seen as a hologram with its three-dimensional richness encoded on two-dimensional boundaries. Finding this theory is like searching for a single key that can open every locked door in the dark mansion of black hole physics, revealing a unified, coherent universe behind the apparent chaos. The event horizon serves as nature's ultimate veil, preserving the universe's predictability. This principle is enshrined in the cosmic censorship hypothesis, a profound and unproven conjecture that suggests the laws of physics abhor a spectacle. It proposes that every gravitational singularity, every point of infinite density, must be permanently hidden from view behind an event horizon. This is not just a matter of cosmic modesty, it is a requirement for the logical order of the cosmos. If a singularity were ever exposed, a so-called naked singularity, the very foundation of scientific prediction would crumble. At a naked singularity, the equations of general relativity break down completely. The fabric of spacetime is not just warped, it is torn, and the rules governing cause and effect would cease to apply. Anything could emerge from such a point with no way to calculate what comes next. Physics as a predictive science would end at its boundary. The universe would contain a place where literally anything is possible, rendering the future fundamentally unknowable. For this reason, most physicists strongly suspect that cosmic censorship is a law of nature, that some mechanism, perhaps quantum gravitational, always steps in to clothe a singularity in an event horizon before it can be seen. Yet, the mathematics of general relativity is tantalizingly permissive. Certain theoretical scenarios, like the overspinning of a Kerr black hole or the collapse of exotic forms of matter, suggest that under very specific and unlikely conditions, an event horizon might not form, leaving the singularity naked to the universe. These are mathematical possibilities, not observed realities, and they often require perfectly symmetrical conditions that are almost impossible to achieve in the messy, real cosmos. The quest to confirm or refute cosmic censorship is a deep philosophical and scientific pursuit. If we could ever observe a naked singularity, perhaps through its gravitational effects on surrounding light and matter, it would be the most disruptive discovery in the history of physics. It would mean that at some point in the universe, the orderly chain of cause and effect is permanently broken and true randomness reigns. This is not the quantum randomness we understand, which is governed by precise probabilities but absolute lawless chaos. For now, the hypothesis stands as a guardian of cosmic order, a belief that the universe keeps its most terrifying secrets safely locked away, ensuring that everywhere we look, the future remains something we can, in principle, strive to understand. The mathematics of a rotating black hole does not end at a point of infinite density. Inside a Kerr black hole, the singularity predicted by general relativity is not a dot but a ring. This ring singularity is a one-dimensional loop of infinite density, a cosmic donut of pure gravitational extremity lying in the equatorial plane. It is the first hint that the interior of a rotating black hole is not a simple pit, but a labyrinth of bizarre geometry. As you fall inward past the event horizon, you enter a region of spacetime so warped by rotation that the roles of space and time do not just bend, they fundamentally swap. In this strange zone, the coordinate we normally call time begins to behave like a spatial direction, and a spatial coordinate begins to behave like time. This is not just a mathematical quirk. It implies that within this region, some paths through spacetime might loop in ways that avoid the central ring altogether. The equations suggest it could be possible to travel on certain trajectories that miss the ring singularity completely, potentially spiraling through the interior and out again, not back into our universe, but into a completely different region of the mathematical solution. These paths are known as closed time-like curves, and they theoretically allow for travel into one's own past, creating the infamous paradoxes of time travel. But is any of this physically real, or is it a phantom in the equations? Most physicists view these intricate interiors as mathematical artifacts, not blueprints for reality. The ring singularity and the regions where time becomes space are supremely unstable. The introduction of even a single particle of real matter, or the application of quantum effects we do not yet understand, would likely cause the entire delicate structure to collapse into chaos, destroying any possibility of a smooth passage. Furthermore, to actually navigate these paths and exit into another universe, you would need to pass through the ring singularity itself, and the gravitational forces there are still infinite, a barrier that seems impassable by any known physics. So we are left with a breathtaking duality. On one hand, the pure mathematics of Einstein's theory paints a picture of a fantastically complex interior, a cosmic labyrinth with gateways to other times and places. On the other hand, the messy, physical universe likely conspires to make that labyrinth inaccessible, collapsing its tunnels and sealing its doors with infinite forces or quantum uncertainty. The true interior geometry remains one of the most speculative unknowns, a shadow cast by our most elegant equations, hinting at a reality so twisted that even the concepts of here and there may lose all meaning before we ever reach the center. The immense gravity of a black hole does more than just pull objects in. It twists the very stage upon which the universe performs. This phenomenon is known as frame dragging or the lens-thirring effect, and it reveals gravity not as a simple force but as the warping and stirring of spacetime itself. Imagine spacetime as a vast, still pool of honey. A non-rotating object like a planet would simply create a deep dimple in that pool, but a spinning object, especially one as massive and fast as a rotating black hole, does something far more dramatic. It reaches into that viscous fabric and stirs it, creating a whirlpool that drags everything nearby along with its rotation. The black hole does not just sit in spacetime, it actively churns it. For any object orbiting close to such a black hole, it is impossible to stand still. The swirling spacetime sweeps it along, forcing it to move in the direction of the spin. This effect has been measured in minute detail around our own rotating Earth by satellites like Gravity Probe B, proving Einstein was right about this subtle prediction. But around a black hole, frame dragging is not subtle. It is a violent, dominant force that shapes entire cosmic environments. The ergosphere, that region just outside the event horizon we mentioned earlier, is a direct product of this extreme frame dragging. Within this zone, spacetime is being pulled around so fiercely that nothing, not even light, can resist the current. To remain stationary relative to distant stars, you would have to travel faster than light itself, which is impossible. You are caught in a cosmic riptide, compelled to move with the twisted flow. This has profound consequences for the black hole's accretion disk and its famous jets. The churning spacetime helps torque up the magnetic fields and funnel material, contributing to the launch of those relativistic beams from the poles. It essentially uses the energy of rotation stored in the twisted spacetime to power the most luminous engines in the cosmos. Yet, when we push our understanding to the very precipice of the event horizon during cataclysmic events like a merger, our models strain. The frame dragging becomes so intense and the warping of spacetime so nonlinear that the mathematics of general relativity becomes extraordinarily difficult to solve. In these moments, spacetime is not just stirred, it is whipped into a chaotic, turbulent froth. We do not yet fully understand the dynamics of this near-horizon maelstrom. How does information about the black hole's spin propagate through this violently churned region? What are the precise limits of how much spacetime can be twisted before something new and unexpected occurs? These are not just questions about black holes, they are questions about the fundamental elasticity and behavior of reality's fabric under the most extreme stress we can conceive. The swirling spacetime around a black hole is a visible expression of its immense energy, but that energy hides a deeper, more fundamental property, a kind of cosmic disorder. This is black hole entropy, and its discovery forced physicists to see these objects in a completely new light. Entropy, in simple terms, is a measure of disorder or the number of microscopic ways a system can be arranged while looking the same from the outside. A neat stack of papers has low entropy, one specific arrangement. That same stack scattered by the wind has high entropy. There are countless ways for the papers to be scattered that all look like a mess. For over a century, the second law of thermodynamics stated that the total entropy of the universe always increases. Things tend toward disorder. Then black holes entered the picture, and they seem to be the ultimate loophole. You could throw a box full of high entropy, like a burning library, into a black hole. From the outside, the black hole would now look only slightly more massive and maybe spinning a bit faster. All that beautiful, complex disorder, all that information, seemed to vanish from the universe, apparently decreasing total entropy and violating a sacred law of physics. This paradox troubled a young physicist named Jacob Bekenstein. His brilliant insight was to propose that black holes themselves must possess entropy and a tremendous amount of it. If a black hole has entropy, then when you throw the disordered library in, the increase in the black hole's entropy could balance out the loss of the library's entropy, saving the second law. Stephen Hawking initially disliked the idea as it suggested black holes had a temperature and should radiate, which he thought impossible. But he soon calculated that they do indeed radiate, leading to his famous Hawking radiation and confirming Bekenstein was right. The formula they developed is stunning in its simplicity and depth. The entropy of a black hole is proportional to the area of its event horizon, not its volume. Specifically, the entropy equals the horizon area divided by 4 in Planck units. This is the Bekenstein-Hawking formula. A single spoonful of matter converted into a black hole would have more entropy than all the stars, planets, and gas clouds in the observable universe combined. This is a number so astronomically huge it defies comprehension. But this answer immediately begs a deeper, more difficult question. In ordinary systems, entropy counts something real. The entropy of a gas counts the number of possible positions and velocities of all its molecules. So what microscopic quantum states is the Bekenstein-Hawking entropy actually counting? What are the hidden, tiny degrees of freedom that make a black hole the most disordered object in existence? We do not know. This is not a minor puzzle, it is a direct window into quantum gravity. The fact that the entropy is tied to the area of a surface, not the volume of a space, is the strongest hint we have for the holographic principle. It suggests that all the information needed to describe everything within the three-dimensional volume of the black hole is actually encoded on its two-dimensional boundary, the event horizon. Think of it like the pixels on a screen. The entropy, the maximum information a black hole can contain, is limited by the number of Planck-sized pixels you can paint on its spherical surface. Each possible configuration of those pixels represents a different microscopic quantum state of the black hole's interior. When you throw the library in, you are not destroying information, you are scrambling it and rewriting it onto this vast spherical hard drive made of spacetime itself. Finding the exact quantum ingredients that make up these pixels, the true atoms of spacetime, is the holy grail of this quest. Some theories, like loop quantum gravity, propose spacetime is woven from tiny, discrete loops, and the entropy counts the number of these loops puncturing the horizon. String theory suggests it counts the quantum states of strings attached to the horizon, like a cosmic fuzzy ball. The correct answer will tell us not just about black holes, but about the fundamental fabric of reality. Why does the universe seem to keep its most complex records on a surface, like a cosmic hologram? The search for the source of black hole entropy is the search for the quantum code from which space, time, and gravity are written. The universe's most durable prisons might not be eternal after all. Given enough time, a black hole can fade away, evaporating into the faintest whisper of radiation. This process, driven by Hawking radiation, unfolds over timescales so vast they dwarf the current age of the cosmos. For a black hole with the mass of our Sun, the journey to nothingness would take about 10 to the 67 years, a number with 67 zeros. Yet this theoretical destiny leads us to a precipice of unknowns, forcing us to confront what happens in the final, violent moments of a black hole's existence. As the black hole shrinks, its temperature rises. A microscopic black hole would be searingly hot, emitting radiation at a furious pace. In its last fraction of a second, it would contain the mass of a mountain compressed into a subatomic volume, and its temperature would soar toward unimaginable levels. This is the domain where quantum gravity must take absolute command, and our current physics offers only speculative glimpses of the end. One possibility is a clean, total disappearance. The black hole evaporates completely, leaving behind only a cloud of thermal Hawking radiation. But this tidy finale resurrects the information paradox in its most acute form. If the black hole and everything that ever fell into it vanish without a trace, then the information describing that matter is permanently erased from the universe. This violates a foundational rule of quantum mechanics, suggesting our understanding is profoundly flawed. To avoid this, physicists have proposed alternative endings. Perhaps the evaporation stops at the very edge of nothingness. The black hole might shrink down to a stable, indestructible speck with a mass near the Planck scale, a remnant that holds all the original information locked inside forever. This cosmic cinder would be a fossil of infinite density, a permanent record of everything the black hole ever consumed. Another, even more radical idea is a phase transition. Just as heating ice transforms it into water, the intense energies of the final evaporation might cause spacetime itself to undergo a fundamental change. The black hole could transform into a different kind of object entirely, something our current theories cannot describe: a wormhole, a gateway to another universe, or a bubble of new vacuum state. The final moment might not be an end, but a rebirth into a different form of reality. These are not just abstract fantasies, they are necessary hypotheses because the classical picture of a smooth evaporation leads to a logical impasse. Observing this process directly is for now beyond our reach. The universe is not old enough for any stellar mass black hole to have reached this late stage. We would need to find a tiny, primordial black hole in its death throes, a search that has so far come up empty. The ultimate fate of a black hole is therefore a question that ties the largest scales to the smallest, linking the destiny of cosmic giants to the quantum nature of gravity. It asks whether the universe allows for true endings, or if every transformation, no matter how extreme, simply rewrites the story in a language we have yet to learn. Deep within the frenzied glow of an accretion disk, a stellar black hole broadcasts a rhythmic, cosmic heartbeat. This is the phenomenon of quasi-periodic oscillations, a rapid and nearly regular flickering in the X-ray brightness observed from matter spiraling toward its doom. The pulses are not perfectly timed like a metronome, hence the term quasi-periodic, but they are far too structured to be random noise. They represent a profound signal from the very edge of the event horizon, a direct probe of spacetime churning under the most extreme gravity imaginable. Astronomers detect these QPOs as specific frequencies in the X-ray light, often appearing in pairs or sets, like distinct musical notes played by the inner accretion disk. The leading theory is that these frequencies are tied to fundamental rhythms of the orbiting plasma. Picture a bell being struck. It rings with a specific tone determined by its size, shape, and material. In the same way, blobs of superheated gas orbiting in the final, most violent orbits near a black hole are subject to three key frequencies. There is the orbital frequency, simply how fast a blob circles the black hole. Then there is the radial frequency, which governs how fast it might oscillate inward and outward if nudged. Finally, there is the vertical frequency, describing how quickly it bobs above and below the disk's plane. In the twisted spacetime of a rotating black hole, these three frequencies are different. The quasi-periodic oscillations we observe are thought to be generated when these fundamental rhythms interact, perhaps through a process called resonance, where one frequency reinforces another, creating a powerful, coherent signal that modulates the X-ray output. But this is where the mystery solidifies. While we can identify the probable notes, we do not understand the instrument. What exact physical mechanism transforms these gravitational rhythms into the specific patterns of flickering light we see? Is it caused by shocks traveling through the magnetized plasma? Do entire sections of the inner disk brightness and dim in unison like a pulsating ring? Or are we seeing the signature of magnetic flares, similar to solar flares but on a scale of immense gravity, repeatedly erupting at a preferred orbital distance? Each model makes different predictions, and the data from observatories like NICER and AstroSat is a cryptic score we are still learning to read. Solving this puzzle is more than an academic exercise. The precise frequencies of these oscillations depend intimately on the mass and spin of the black hole itself. If we can definitively decode the mechanism, QPOS could become one of the most precise tools in astrophysics, allowing us to weigh and measure the spin of stellar black holes with unprecedented accuracy, simply by listening to the rhythmic ticks of light from their final orbits. For now, that steady, rapid flicker remains a message from the brink, a complex code sent by matter dancing to the fundamental frequencies of warped spacetime, its full meaning still just beyond our grasp. Between the stellar mass black holes born from dying stars and the supermassive giants anchoring galaxies, a cosmic gap remains. Where are the middleweights, the intermediate mass black holes with hundreds or thousands of solar masses? Their existence is a critical missing link in the black hole family tree, and the hunt for them has turned into one of astronomy's most compelling detective stories. The evidence is tantalizing but indirect, pointing to shadows in the data. One key clue comes from mysterious objects known as ultraluminous X-ray sources. These are spots within distant galaxies that shine with the X-ray brightness of millions of suns, far too luminous to be explained by a typical stellar mass black hole feeding from a companion star. The physics suggests an object more massive than a star, yet smaller than a galactic nucleus, could be responsible. A potential intermediate mass black hole on a cosmic feeding frenzy. Another powerful line of evidence echoes from the void itself. Gravitational wave observatories have begun detecting mergers with a final mass that falls squarely into this intermediate range. Signals like GW190521, which produced a black hole of about 150 solar masses, are smoking guns. They prove that nature can and does forge black holes too heavy to come from a single collapsing star, yet too light to be considered supermassive. The very detection of such an object was a landmark, confirming a whole new class, but their formation pathways are shrouded in mystery. How does the universe build these mid-sized monsters? One leading theory takes us into the heart of dense globular clusters, ancient swarms of hundreds of thousands of stars. In such a crowded environment, runaway collisions could occur. Multiple massive stars might merge together over time, creating a behemoth star that then collapses directly into an intermediate mass black hole. Alternatively, a small black hole seed at the cluster's core could act as a gravitational bully, sinking through the cluster, gobbling up stars and growing steadily over billions of years. Another possibility reaches back to the dawn of time. The very first stars, known as population 3 stars, are thought to have been colossal, perhaps hundreds of times the mass of our Sun. When these primordial giants died, they may have left behind black hole seeds that were already intermediate in mass, providing a ready-made foundation for later growth. Each formation path leaves a different fingerprint on the black hole's environment and its subsequent behavior, clues we are only now learning to read. Finding and studying these elusive objects is crucial. They could be the building blocks of supermassive black holes, the missing rungs on the ladder of cosmic structure. Do they mostly dwell in the cores of dense star clusters, or do they wander freely through galactic halos? Are they the ancient remnants of the first stars, or the products of later cosmic violence? Each confirmed intermediate mass black hole is a piece of the puzzle, helping us understand how gravity sculpts the universe across all scales, from the death of a single star to the birth of a galactic empire. Just outside the point of no return lies a zone of final commitment, a place where the last threads of resistance are broken. This is the plunging region, a thin shell of space immediately outside the event horizon where matter, having spiraled for eons in the accretion disk, finally gives up its orbital struggle and plunges straight inward. It is a cosmic waterfall's edge, where the flow of spacetime itself becomes so steep and swift that nothing can hold back. Within this violent transition, magnetic fields face their ultimate test, and our understanding of physics reaches its breaking point. These fields are not mere spectators, they are the architects of the black hole's most spectacular displays, the very conduits that channel energy into the relativistic jets that scar the cosmos. But to do that, they must survive and operate in an environment where the rules are written in a language we are still learning to speak. The plunging region is a maelstrom where three formidable branches of physics collide. First, there is the overwhelming gravity described by Einstein's general relativity, which warps spacetime into a frenzied river dragging everything toward the horizon. Second, there is the behavior of superheated magnetized plasma, governed by the complex laws of magnetohydrodynamics. And third, lurking at the very smallest scales, are almost certainly quantum effects that become significant in such an extreme gravitational field. Trying to model how magnetic fields behave here is like trying to predict the exact pattern of spray at the base of Niagara Falls, while accounting for the molecular bonds of every water droplet, all while the ground beneath you is falling away at near light speed. One of the central puzzles is magnetic reconnection. In simpler environments like the Sun's corona, when magnetic field lines break and reconnect, they release tremendous explosive energy in solar flares. In the plunging region, this process is turbocharged by gravity. Field lines are stretched, twisted, and snapped with phenomenal violence. Does this reconnection help launch the jets by flinging particles outward along the magnetic channels? Or does most of the energy released here simply get dragged across the horizon, lost forever from our universe? We do not know. Furthermore, the fields are likely amplified to unbelievable strengths, potentially becoming dynamically important, meaning they can push back against the flow of spacetime and alter the very geometry of the plunge. This creates a feedback loop of immense complexity. The magnetic fields shape the infall of matter, and the infalling matter in turn twists and strengthens the fields. It is a self-feeding storm where every element influences every other, and our computer simulations struggle to capture the full, turbulent reality. The plunging region is thus the black hole's final workshop, the chaotic forge where the raw gravitational power of infalling mass is partly converted into the directed fury of its jets. To understand it is to understand the engine's ignition switch. Yet for now, it remains a theoretical frontier, a place of shadow and inference where our equations flicker and fail, hinting at a deeper order in the chaos just before the dark. The deepest mysteries of black holes may reach far beyond their own event horizons, intertwining with the ultimate fate of the cosmos itself. This leads to one of the most radical and speculative ideas in modern cosmology, a potential link between the infinitesimal singularities of black holes and the vast, accelerating expansion of the entire universe, driven by the force we call dark energy. At first glance, these concepts could not seem more different. Black holes represent the ultimate concentration of matter and energy, regions of immense, localized gravity that pull everything inward. Dark energy, on the other hand, is a smooth, repulsive force that permeates all of empty space, causing galaxies to fly apart from one another at an ever-increasing rate. One is a cosmic trap, the other a cosmic repeller. Yet some theoretical physicists propose these opposites might be two sides of the same coin, connected through the enigmatic properties of the vacuum. The central clue lies in the cosmological constant, a term Einstein originally introduced into his equations to keep the universe static, and later called his greatest blunder. Today, it is the leading candidate to explain dark energy, representing a constant energy density inherent to empty space itself. This vacuum energy exerts a negative pressure, pushing the universe apart. The monumental puzzle is why this constant has the incredibly tiny but precisely tuned value we observe. One provocative conjecture suggests that the source of this vacuum energy might not be spread evenly, but could be tied to specific, extreme locations in spacetime. Enter the black hole singularity. In the realm of quantum field theory, the vacuum near any mass is not empty, it seethes with fluctuating energy. At a singularity where curvature becomes infinite, these quantum vacuum fluctuations could be magnified to an extreme degree. Could it be that the collective effect of all the singularities inside all the black holes across cosmic history contributes to, or even generates, the overall cosmological constant we measure? In this view, each black hole is not just a consumer of matter, but a generator of repulsive vacuum energy, its intensely warped core acting as a wellspring for the force that drives the universe apart. This idea forms a breathtaking, if highly speculative, bridge. It connects the physics of the unimaginably small, the quantum gravity of a singularity, to the behavior of the unimaginably large, the accelerating expansion of the cosmos. It suggests that the same objects that create the most powerful gravitational pulls locally might also be seeding the repulsive force that dominates the universe globally. Framing this connection requires us to rethink the universe as an interconnected web, where the most extreme objects are not isolated anomalies, but integral components of the cosmic engine. If true, the growth of black holes over time would be subtly linked to the evolution of dark energy. As more black holes form and grow, perhaps through galactic mergers, their collective contribution to the vacuum energy might change, slowly altering the expansion rate of the universe itself across billions of years. This remains a fringe hypothesis far from the mainstream and faces significant mathematical and conceptual hurdles, yet its power lies in its ambition. It dares to ask if the two greatest puzzles in cosmology, the nature of black hole singularities and the origin of dark energy, might share a single, profound solution. It challenges us to see the cosmos not as a collection of separate phenomena, but as a single, dynamic entity where the darkest hearts of galaxies whisper to the void between them, shaping the destiny of everything. These cosmic giants are not just destinations, they are the most extreme laboratories nature has ever built. Within their immense gravitational fields and at the precipice of their event horizons, conditions exist that we could never hope to recreate on Earth. This makes black holes a unique testing ground, a place where we can search for physics beyond our current rulebook, the Standard Model. This framework has been spectacularly successful, describing 3 of the universe's 4 fundamental forces and all known particles. But it has glaring holes. It does not include gravity, it cannot explain dark matter, and it leaves key questions about the universe's earliest moments unanswered. To find what lies beyond, we need to push matter and energy to their absolute limits, and nothing does that better than a black hole. One of the most tantalizing probes is the search for extraspatial dimensions. In our everyday experience, we perceive 3 dimensions of space and 1 of time, but some theories, like string theory, suggest there could be more tiny dimensions curled up at a scale far smaller than an atom. These hidden dimensions could explain why gravity is so weak compared to the other forces. On Earth, these extra dimensions would be invisible, but near a black hole, gravity becomes unimaginably strong. If extra dimensions exist, they would modify how gravity behaves at these extreme scales, changing the way black holes evaporate via Hawking radiation. A black hole evaporating into extra dimensions would do so faster and at a different temperature than one confined to our familiar 3-dimensional space. While we have not yet seen a black hole evaporate, we can look for other signatures. The precise ring-down tones of a merged black hole, detected through gravitational waves, are exquisitely sensitive to the number of dimensions in our universe. Any deviation from the predictions of general relativity in 4 dimensions could be a whisper from a hidden, compacted geometry. Black holes also offer a potential window into dark matter. One leading candidate for this invisible substance is a hypothetical particle called the action. If actions exist, they could be produced in vast numbers in the intense magnetic and gravitational fields surrounding certain black holes, particularly those with strong magnetic fields like the one at our galaxy's center. These actions would then decay into pairs of photons, creating a faint but potentially detectable radio signal emanating from the black hole's vicinity. It is like tuning a cosmic radio to a specific frequency, listening for the signature hum of dark matter being born from the dark heart of our galaxy. Furthermore, the search for supersymmetry, a theory that proposes a partner particle for every known particle, could get a boost from black hole mergers. The final mass and spin of a merged black hole depend on the total energy carried away by gravitational waves and any other particles that might be produced. If exotic, supersymmetric particles were created in the violent collision, they would carry away extra energy, subtly changing the final properties of the remnant black hole in a way that might be discernible in future, ultra-precise gravitational wave observations. Every observation we make of a black hole, from the flicker of its X-ray heartbeat to the thunderclap of its collisions, is a data point in an experiment of cosmic scale. We are not just watching distant objects, we are running tests on the fabric of reality itself, using gravity's most perfect traps as our apparatus. A single anomaly in the expected signal, a deviation in a ringdown frequency, or an unexpected glow from an event horizon could be the clue that cracks the standard model wide open, revealing a deeper, more complete universe waiting just beyond the veil of our current understanding. But even the most absolute boundary in the universe must face the test of time. The event horizon, that perfect one-way membrane, is not a static wall but a dynamic surface shaped by the black hole's entire future. This introduces a subtle but profound question about its fundamental stability. Could this horizon ever be disrupted or even erased under the right conditions? The mathematics of general relativity suggests the horizon is remarkably robust against small disturbances, like tossing a pebble into a pond. These are called perturbations. If you throw matter or energy at a black hole, the horizon will bulge and ripple, but it quickly settles back into a smooth, spherical shape, absorbing the new material and growing slightly larger. The horizon is self-healing, swallowing any attempt to puncture it and incorporating the disturbance into its new, stable form. This resilience is a key feature of these cosmic objects. Yet, theorists must consider more extreme scenarios that push the rules to their breaking point. One such scenario involves the ultimate fate of the cosmos. Our universe is not just expanding, it is accelerating, driven by the mysterious force of dark energy. In a future so distant it defies imagination, this acceleration could become so dominant that all galaxies beyond our local group vanish over the cosmic horizon, and the universe becomes a cold, empty void. In such a lonely epoch, a black hole would be completely isolated with no new matter or energy to consume. It would slowly evaporate via Hawking radiation, growing smaller and hotter until its final quantum demise. But here is the peculiar twist. The event horizon is not defined by what is happening right now. It is defined by the black hole's entire future history, a concept physicists call teleological. The horizon exists today because we know, in principle, that light emitted from just inside a certain radius will never escape in the infinite future. But if the black hole is destined to fully evaporate in a finite time, does that change the nature of its horizon from the very beginning? Some analyses suggest that in a universe dominated by dark energy, the horizon of an isolated, evaporating black hole might not form in the classical sense at all, or it could become a transient feature. The black hole might be, in a cosmic sense, starving from birth, its destiny to vanish altering the very definition of its boundary. This is not a flaw in the theory, but a revelation of its depth. It tells us that a black hole is not an isolated object you can examine under a static light. It is a process, a story written in spacetime from its violent birth to its speculative end. The stability of its defining feature, the event horizon, is therefore tied to the ultimate fate of the cosmos itself. It forces us to see the black hole not as a permanent prison, but as a dynamic entity in a changing universe where the most absolute line we can conceive is drawn not just by gravity, but by the arrow of time and the destiny of all things. The profound stability of a black hole's horizon is challenged by a stranger, more fundamental connection, one that links the vast geometry of spacetime to the ghostly bonds of the quantum world. This is the realm of quantum entanglement, a phenomenon so bizarre Einstein famously called it spooky action at a distance. It describes how two particles can be linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are in the universe. For decades, this was seen as a curiosity of the small scale, separate from the grand theater of gravity. But today, that wall is crumbling and black holes are at the center of the demolition. The most provocative bridge is a conjecture known as ER equals EPR. It proposes a breathtaking equivalence. The ER stands for Einstein-Rosen, the wormholes hidden in the equations of general relativity. The EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted the paradox of quantum entanglement. The idea suggests these are not two different things, but two descriptions of the same underlying reality. A wormhole, a tunnel through spacetime, might be the geometric manifestation of quantum entanglement. In this view, two entangled black holes would not be separate objects connected by some invisible force, but a single connected spacetime geometry, a wormhole linking their interiors. This is not a tunnel you could travel through. It is a microscopic quantum bridge, but its existence would mean that entanglement literally weaves the fabric of spacetime itself. This leads to a radical reimagining of a black hole's interior and its evaporation. Imagine a black hole that has been evaporating for eons via Hawking radiation. The radiation particles escaping to infinity are entangled with their partners that fell into the black hole long ago. But as the black hole shrinks, a problem arises. Quantum mechanics has a strict rule: you cannot just copy or clone entanglement. The new Hawking radiation particles emitted later must also become entangled with the black hole's remaining interior. This creates a complex web, a supposed violation of quantum rules known as the monogamy of entanglement. The ER equals EPR conjecture offers a stunning escape. It proposes that as the black hole evaporates, the interior is not a separate place at all. Instead, it becomes holographically encoded in the intricate pattern of entanglement among all the Hawking radiation particles that have ever left. The interior space, with all its apparent volume, is an illusion generated by the quantum connections between the radiation quanta dancing in the void. The black hole's inside is not behind you, it is in the relationships between the particles in front of you. This transforms the information paradox into a question of translation. Information is not lost, it is scrambled from a geometric language, the interior of the black hole, into an informational language, the entanglement of the radiation. The event horizon is the translator's desk. These ideas remain deeply speculative, a set of clues scribbled at the intersection of our two greatest theories. They suggest that to understand the fate of information in a black hole, we must first understand how space itself emerges from something more primitive, a vast quantum network of entangled connections. It paints a picture where the universe is not built of things in places, but of relationships between things. The immense gravity of a black hole, then, is not a force pulling on objects in space, but a manifestation of the deepest, most complex entanglement the cosmos can produce. It is a hint that when we finally peer past the event horizon, we might not find a place, but a pattern, the ultimate expression of quantum connection written in the language of gravity. Their final unknown is also the most expansive, reaching across the entirety of cosmic time. We have explored black holes as engines, puzzles, and destroyers, but what is their ultimate purpose in the grand narrative of the universe? Are they merely temporary features, cosmic scars that will one day fade from existence, or do they play a deeper, more permanent role in the order of things? This question pushes us beyond observation and into the realm of profound speculation, where cosmology meets philosophy. One possibility is that they are indeed endpoints, the universe's ultimate recyclers that eventually erase themselves and all they consume through Hawking radiation. In this view, black holes are a temporary phase, a way for matter to reach its most dense state before dissipating into a faint, cold mist of particles over timescales so vast they have no practical meaning. The cosmos would eventually become a thin, dark sea dotted with the last glowing embers of evaporating black holes, a quiet and final chapter. But another, far more dramatic idea suggests they are not ends but beginnings. The concept of cosmological natural selection proposed by physicist Lee Smolin imagines black holes as cosmic wombs. When a black hole forms a singularity, the extreme conditions at its heart might trigger a new Big Bang, birthing an entirely new universe inside it with physical constants slightly different from our own. In this breathtaking scenario, our entire cosmos could be the interior of a black hole residing in a parent universe, and every black hole we see could be spawning its own cosmic lineage. Universes that produce more black holes would have more offspring, leading to a form of natural selection favoring laws of physics that are prolific black hole producers. Our own universe, rich with galaxies and stellar collapses, might be a highly fit member of this multiverse family tree. A related idea comes from bounce or cyclic universe models. Perhaps when our universe reaches its final state of maximum entropy, a vast sea of radiation and evaporating black holes, the collective quantum fluctuations in this uniform sea could spontaneously trigger a new cosmic contraction, a big bounce that births the next cycle. In this model, black holes are not the architects of the bounce, but key ingredients in the cosmic broth that makes it possible. Their evaporated information providing the seeds for structure in the next iteration. Each of these speculations carries a different meaning for the fate of information and the nature of reality. If black holes are final erasers, then information and structure are truly transient. If they are cosmic seeds, then information might be reborn, transformed, and passed on in an endless chain of cosmic generations. The role we assign to them defines the story we tell about existence itself. For now, their ultimate purpose remains a blank page in the book of the cosmos. They are the darkest punctuation marks in the narrative of spacetime, and we cannot yet read the sentence they conclude or begin. This final unknown reminds us that to understand black holes is to ask not just how the universe works, but why it is here at all, and what story it is trying to tell in the silent, gravitational language of the void. These 30 unknowns are not a checklist of ignorance, but a map of the frontier. Each mystery, from the silent singularity to the fading whisper of Hawking radiation, is not an isolated puzzle. They are threads in a single, magnificent tapestry, all pulling toward a common horizon, a complete theory of quantum gravity. The paradox of information lost challenges the smooth geometry of the event horizon. The search for primordial black holes whispers of the universe's first moments. The precise spin of a galactic giant hints at the limits of spacetime itself. Every question interlocks with another, revealing that to solve one is to gain a clue for all the rest. Black holes have taught us that our universe is far stranger and more connected than we ever dreamed. They are not cosmic dead ends, but luminous signposts. They point beyond Einstein, beyond the standard model, into a realm where space, time, and information are woven from something more fundamental. Our journey through these unknowns is in essence the story of science itself. It is the story of looking into the darkest places and finding not an end to our questions, but the beginning of new ones. It is a testament to human curiosity that we can take the most absolute voids and from them draw a deeper understanding of reality. The quest continues with every gravitational wave detected, every flicker of X-ray light analyzed, and every new simulation on a supercomputer. This story is still being written, and you are here to witness it. To follow along with the next chapter, keep looking up and keep wondering. The greatest discoveries are still hidden in the dark, waiting for the light of a question to find them.